Hello there, and welcome to another peaceful journey through the cosmos. Tonight, we're drifting away from the rush of daily life and floating gently into the serene world of comets. Those ancient wanderers that have been silently gliding through space for billions of years, carrying stories older than our planet itself. As you settle in for the evening, let your breathing slow and your mind soften. We're about to explore some of the most soothing and fascinating truths about these celestial travelers. Facts that will carry you on a gentle current of wonder, like watching snow fall on a quiet winter night. Each revelation will be a soft stepping stone across the tranquil waters of space, guiding you toward rest. If you find these cosmic lullabies as calming as I do, feel free to like this video and subscribe for more nighttime explorations of the universe. But for now, all you need to do is get comfortable. Let the gentle hum of discovery wash over you as we begin this peaceful voyage among the comets. Comets are among the most ancient objects in our solar system. They formed over 4.5 billion years ago, in the earliest days when the sun was just beginning to shine and the planets were still taking shape. These frozen time capsules have been drifting through the outer reaches of space ever since, largely unchanged from their original form. When you look at a comet, you're seeing matter that predates nearly everything else around us. The water ice, the dust, the simple organic compounds, all of it has remained frozen and preserved in the cold depths of space, waiting patiently for its moment to shine. Think of comets as cosmic snow globes, carrying within them the pristine materials from which our entire solar system was born. They hold the building blocks of planets, the seeds of oceans, and perhaps even the ingredients that sparked life itself. In their quiet journey through the darkness, they carry the memory of creation itself, a gentle reminder that everything around us, including ourselves, emerged from stardust and ancient ice. Most comets spend their lives in a vast, invisible cloud that surrounds our solar system. This region, called the Oort cloud, stretches so far from the sun that its edge nearly touches the nearest stars. It's a peaceful realm where temperatures hover just above absolute zero, and time moves differently than it does here on Earth. Trillions of comets drift slowly through this cosmic sanctuary, taking hundreds of thousands of years to complete a single orbit around our distant sun. In the Oort cloud, there is no day or night, no seasons, no weather, just the eternal dance of gravity and motion, playing out across distances so vast that light itself takes months to cross from one side to the other. It's perhaps the most serene place in our solar system, where comets rest in their frozen slumber, undisturbed by the chaos and activity of the inner planets. Occasionally, something gentle disturbs this tranquil realm. Perhaps a passing star tugs softly on a distant comet, or the subtle gravitational influence of the galaxy itself nudges one of these sleeping giants toward the inner solar system. When this happens, a comet begins its slow, graceful journey toward the sun, a voyage that can take millions of years to complete. As a comet travels inward, it remains completely frozen and inactive for most of its journey. For decades or even centuries, it appears as nothing more than a dark, rocky snowball drifting silently through space. There's something deeply peaceful about this phase of a comet's life, when it moves through the cosmos like a ship sailing across a calm, dark ocean under a starlit sky. But as the comet draws closer to the warmth of the sun, a beautiful transformation begins. The frozen gases on its surface start to sublimate, turning directly from ice into vapor without ever becoming liquid. This process happens so gradually, so gently, that it's like watching a flower bloom in extreme slow motion. The comet begins to develop what astronomers call a coma, a soft, glowing atmosphere of gas and dust that surrounds the nucleus like morning mist rising from a quiet lake. The coma grows larger and more luminous as the comet continues its approach. What started as a frozen ball of ice and rock, perhaps only a few kilometers across, becomes surrounded by a glowing cloud that can stretch for hundreds of thousands of kilometers. Yet despite its enormous size, the coma is incredibly tenuous, more rarefied than the best vacuum we can create on Earth. If you could somehow stand within it, you would barely notice its presence, save for the faint sparkle of dust particles catching the sunlight. As the comet ventures even closer to the sun, the most magical part of its transformation begins. The solar wind, that constant stream of particles flowing outward from our star, begins to push against the coma, sculpting it into the comet's most famous feature, its tail. Actually, comets develop two tails, each one formed by different materials and shaped by different forces. The first tail, made of ionized gas, is pushed directly away from the sun by the solar wind. This ion tail glows with a blue-green light, created when solar radiation excites the gas molecules, causing them to emit photons like a gentle aurora stretching across millions of kilometers of space. The ion tail always points away from the sun like a cosmic weather vane indicating the direction of the solar wind. The second tail is made of dust particles that have been lifted from the comet's surface by the sublimating gases. These particles are larger and heavier than the ionized gas, so they're not pushed as directly by the solar wind. Instead, they follow the comet's orbital path, creating a curved tail that traces the comet's journey through space like the wake of a ship sailing through celestial waters. Both tails are incredibly beautiful and surprisingly delicate. Despite stretching for millions of kilometers, they contain less material than the air in a small room. They're more like whispers of matter, visible only because they scatter and emit sunlight across vast distances. When the comet begins its journey back toward the outer solar system, these magnificent tails gradually fade and disappear, leaving the comet to return to its frozen, dormant state. The nucleus of a comet, the solid core beneath all the gas and dust, is often described as a dirty snowball. But this simple description doesn't capture the true poetry of these ancient objects. Each nucleus is unique, shaped by billions of years of slow formation in the outer reaches of the solar system. Some are smooth and rounded, others are lumpy and irregular, covered with hills and valleys, craters and ridges that tell the story of countless gentle collisions with other small bodies. The surface of a typical comet nucleus is darker than charcoal, coated with a layer of organic compounds that have been slowly processed by cosmic radiation over eons. Beneath this dark crust lies a mixture of water ice, frozen carbon dioxide, frozen methane, and countless tiny particles of rock and dust. It's like a cosmic fruitcake, with ingredients from across the solar system mixed together and preserved in the deep freeze of space. When scientists study pieces of comets that have fallen to Earth as meteorites, they find some of the most primitive materials in the solar system. Tiny grains that predate the formation of our sun, organic molecules that might have seeded early Earth with the building blocks of life, and isotopic signatures that tell us about conditions in the stellar nursery where our solar system was born. Comets follow highly elliptical orbits that carry them from the cold outer reaches of the solar system to the warm inner regions near the sun. then back out again. These orbits can take anywhere from a few years to millions of years to complete, depending on where the comet originated and how it was nudged toward the inner solar system. Short-period comets, like the famous Halley's Comet, complete their orbits in less than 200 years. They've made this journey many times before, gradually losing material with each passage near the Sun. Their orbits have been rounded and shortened by gravitational interactions with the giant planets, particularly Jupiter, which acts like a cosmic shepherd, capturing comets and guiding them into more regular paths. Long-period comets arrive from the distant Oort cloud on orbits that can take millions of years to complete. When we see one of these visitors, we're witnessing something that may not return to the inner solar system for countless generations. They're like cosmic postcards from the deep frontier of our solar system, carrying news from regions so distant that the Sun appears as just another star in the sky. There's something profoundly peaceful about contemplating these vast orbital timescales. While we measure our lives in decades, comets measure theirs in millennia and beyond. They're patient travelers, content to spend eons in the cold darkness between brief moments in the sun's warmth. Their rhythm is the rhythm of deep time itself, a gentle reminder that the universe operates on scales far grander than our daily concerns. The beauty of comets has inspired humans throughout history. Ancient civilizations saw them as omens and portents, not understanding their true nature but recognizing their otherworldly magnificence. Medieval observers called them hairy stars because of their flowing tails, and even today, when we understand the science behind their appearance, comets retain their power to evoke wonder and contemplation. When a bright comet appears in our skies, it connects us to something larger than ourselves. For a few weeks or months, we share the night sky with a visitor from the deep cosmos, a wanderer that has traveled unimaginable distances to grace us with its presence. In that shared moment, under the same stars, we become part of a story that stretches back to the very beginning of our solar system. The water that flows in our oceans and falls as rain may have first arrived on Earth, carried within the hearts of comets. Billions of years ago, during a period called the Late Heavy Bombardment, countless comets and asteroids pelted the young Earth, delivering vast quantities of water and organic compounds to our planet's surface. Each impact was like a cosmic delivery, bringing the essential ingredients that would eventually allow life to flourish. Scientists have discovered that the water in some comets has a chemical signature remarkably similar to Earth's oceans. The ratio of heavy water to regular water, the presence of certain dissolved gases, even the types of organic molecules found in cometary ice, all point to a deep connection between these wandering ice balls and the blue world we call home. It's a beautiful thought that every glass of water you drink, every raindrop that touches your skin, may once have been frozen solid in a comet drifting through the darkness beyond Pluto. This connection makes comets more than just pretty lights in the sky. There are cosmic relatives, distant cousins that help shape the very environment that gave rise to life. When you watch a comet's tail streaming across the heavens, you're looking at the same materials that helped fill Earth's first oceans and may have delivered the chemical living things, eventually building blocks from which all emerged. The journey of water from comet to ocean spans billions of years and distances that challenge imagination. A single water molecule might spend eons frozen in a comet's nucleus, traveling in the cold silence of the outer solar system. Then, in one brief, brilliant moment, That molecule sublimates into the comet's coma, catches the light of the sun, and becomes part of the spectacular display we see from Earth. Eventually, through processes we're only beginning to understand, some of that water finds its way to planets like ours, where it pools in basins and flows in rivers, carrying with it the memory of its cosmic origins. Comets are surprisingly fragile objects, held together by little more than their own weak gravity and the binding power of ice. Despite appearing solid and permanent in photographs, they're actually more like loosely packed snow than solid rock. If you could somehow transport a comet nucleus to Earth and set it down gently on the ground, it might simply fall apart under its own weight, crumbling into a pile of dust and ice crystals. This delicate nature means that comets are constantly changing, constantly evolving. Each time they pass near the sun, they lose a little bit of themselves to space. The solar wind strips away gases from their comas, and tiny dust particles drift away into the void, creating the beautiful tails we admire, but also gradually diminishing the comet itself. Over many orbital cycles, a comet slowly wastes away, like a bar of soap dissolving in warm water. Some comets experience more dramatic changes during their lifetimes. The gentle warming of the sun can cause pockets of volatile gases trapped deep within the nucleus to suddenly vaporize, creating jets of material that spray out into space. These jets can actually change the comet's orbit slightly, acting like tiny rocket engines that push the comet in unexpected directions. Occasionally, the stress of these outgassing events can cause a comet to split apart entirely, creating multiple smaller comets that follow similar paths through the solar system. The famous comet Shoemaker-Levy 9 experienced such a breakup, but in its case, the cause was the immense gravitational pull of Jupiter. The giant planet's gravity stretched and twisted the comet until it tore apart into more than 20 fragments, each following the same doomed trajectory toward collision with Jupiter. When those fragments finally struck the planet in 1994, they created a series of dark scars in Jupiter's atmosphere that were visible for months, each mark larger than Earth itself. Even in their destruction, comets teach us about the gentle forces that shape our solar system. The same gravitational influences that can tear a comet apart also guide its path through space, creating the beautiful elliptical orbits that bring these visitors close enough for us to see. It's a reminder that in space, as in life, creation and destruction are often two sides of the same cosmic coin. The dust that comets leave behind during their journeys doesn't simply vanish into nothingness. Instead, it spreads out along the comet's orbital path, creating streams of tiny particles that Earth encounters at regular intervals throughout the year. When our planet passes through one of these cosmic debris fields, we're treated to meteor showers. Those peaceful celestial fireworks displays that light up the night sky with streaks of burning dust. Each meteor you see during a shower, like the Perseids or the Geminids, is a tiny fragment of ancient comet, no larger than a grain of sand. That's D. This atmosphere at incredible speed entering Earth, friction with our air causes these particles to heat up and glow, creating those brief trails beautiful of light that have inspired countless wishes and dreams. In a very real sense, when you watch a meteor shower, you're seeing pieces of comets from the distant past burning up in celebration above your head. The predictable nature of these meteor showers reflects the orderly dance of celestial mechanics. Year after year, Earth returns to the same points in its orbit, encountering the same streams of cometary debris at the same times. The Perseids always peak in mid-August, the Geminids in mid-December, as reliable as the changing seasons. There's something deeply comforting about this cosmic punctuality, a reminder that despite all the chaos and uncertainty in our daily lives, the universe follows patterns we can understand and predict. Some of the most spectacular comets in history have left lasting impressions not just in the sky, but in human culture and memory. The Great Comet of 1811 was visible to the naked eye for over a year, inspiring poetry and art throughout Europe and America. Comet McNaught in 2007 became so bright that it could be seen even in daylight, its magnificent tail stretching across a quarter of the sky for observers in the southern hemisphere. But perhaps no comet is more famous than Halley's Comet, that faithful celestial timekeeper that returns to grace our skies every 75 to 76 years. Records of Halley's appearances stretch back over 2 millennia, making it one of the most well-documented objects in astronomy. Chinese astronomers recorded its passage in 240 BC, and it appeared prominently in the Bayating, the Norman Conquest of Faux, tapestry Commemore 1066, where it was interpreted as an omen of the coming invasion. The regularity of Halley's orbit makes it a cosmic clock, marking the passage of human generations with its periodic returns. People who witnessed its appearance in 1910 were gone by the time it returned in 1986, but their children and grandchildren were there to welcome it back. Those who saw it in 1986 may live to see its next return in 2061, creating a personal connection that spans decades of life. This generational aspect of comet watching adds a deeply human dimension to what might otherwise be purely scientific observations. Somewhere in your family history, there were ancestors who looked up at the same comet you might see today, experiencing the same sense of wonder and mystery that you feel. The comet serves as a bridge across time, connecting you to people you'll never meet, but with whom you share this cosmic experience. Modern space exploration has allowed us to study comets more closely than ever before. Spacecraft have flown through comet tails, landed on comet surfaces, and even crashed into comets to study the material thrown up by the impact. These missions have revealed comets to be far more complex and interesting than the simple, dirty snowballs scientists once thought them to be. The European Space Agency's Rosetta mission spent 2 years orbiting Comet 67P, watching as it came to life during its approach to the Sun. The spacecraft's cameras captured images of jets of gas and dust streaming from the comet's surface, creating shadows and weather patterns in the thin atmosphere around the nucleus. The mission even deployed a small lander named Philae, which became the first human-made object to successfully soft land on a comet's surface. These close-up studies have revealed that comets are geologically active worlds in miniature, with cliffs and boulders, smooth plains, and rough terrain. Some regions of a comet's surface are surprisingly smooth, while others are covered with strange, angular rocks that look like abstract sculptures carved by the solar wind. The diversity of landscapes on these small objects reminds us that every world in our solar system, no matter how small or distant, has its own unique character and history. Deep within the heart of every comet lies a record of the early solar system, preserved in ice and dust, that has remained unchanged for billions of years. When scientists analyze samples of cometary material, they find organic compounds that might have been the precursors to life, along with minerals that formed in the cold depths of interstellar space before our sun was even born. Each comet is like a library book from the dawn of time, written in a language of chemistry and physics that we're only beginning to learn to read. The study of these ancient materials helps us understand not just how our solar system formed, but how planetary systems in general come into being around other stars. The same processes that created comets in our outer solar system are likely happening around young stars throughout the galaxy, creating new populations of icy wanderers that will someday carry water and organic compounds to whatever planets may form in those distant systems. This cosmic perspective transforms our understanding of comets from mere curiosities in the night sky to essential players in the grand story of life in the universe. They're not just beautiful objects to admire during rare appearances, but active participants in the ongoing process of planetary formation and the distribution of life's building blocks across the cosmos. As you drift toward sleep tonight, let your mind wander among these ancient travelers, these patient carriers of water and stardust, who've been quietly shaping the story of life for billions of years. In their gentle orbits and spectacular displays, in their fragile beauty and cosmic importance, comets remind us that we are all part of something much larger and more wonderful than we often remember in the rush of daily life. The tails of comets always point away from the sun, regardless of the direction the comet is traveling. This creates one of the most enchanting phenomena in our solar system. When a comet is approaching the sun, its tail streams behind it like the wake of a ship. But as the comet rounds the sun and begins its journey back to the outer reaches of the solar system, something magical happens. The tail doesn't follow behind the comet anymore. Instead, it leads the way, flowing ahead of the nucleus like a cosmic banner announcing the comet's passage through space. This reversal happens because the tail isn't created by the comet's motion through space, but by the steady pressure of the solar wind pushing gas and dust away from the sun. It's a gentle but constant force, like an invisible hand guiding these delicate streams of matter into their elegant configurations. The result is a celestial dance where the comet appears to be both chasing and fleeing from its own luminous appendage, creating an ever-changing spectacle across the darkness. The longest comet tail ever recorded stretched for over 350 million kilometers, more than twice the distance from Earth to the Sun. This magnificent streamer belonged to the Great Comet of 1843, whose tail was so extensive that it spanned 70 degrees across the sky when viewed from Earth. To put this in perspective, if you held your arms straight out to your sides, the comet's tail would have stretched from one hand to the other and beyond. For observers at the time, it must have seemed as though the heavens themselves were unfurling a celestial ribbon across the night sky. Such enormous tails are possible because of the incredible thinness of the material they contain. If you could somehow gather all the gas and dust in that 350 million kilometer tail and compress it into a solid ball, it would likely be no larger than a mountain on Earth. The tail appears substantial only because it scatters sunlight across such vast distances, creating the illusion of solid structure, where there is mainly empty space sprinkled with the faintest whisper of matter. This ethereal nature of comet tails makes them sensitive to the smallest changes in the solar wind. When the sun experiences solar flares or other disturbances, the effects ripple outward at the speed of light, reaching distant comets and causing their tails to flutter and dance like flags in a cosmic breeze. Astronomers have observed comet tails bending, twisting, and even temporarily disappearing as they respond to these subtle changes in the sun's output. It's as though each comet carries its own delicate barometer, measuring and displaying the sun's moods across millions of kilometers of space. Some comets develop multiple tails simultaneously, creating spectacular displays that can stretch in different directions at once. The most famous example is Comet Hale-Bopp, which graced our skies in 1997 with two distinct tails that were easily visible to the naked eye. The blue ion tail pointed directly away from the sun, while the yellowish dust tail curved gently along the comet's orbital path. Together, they created a celestial sword of light that dominated the evening sky for months, inspiring millions of people to step outside and reconnect with the cosmos above. The colors in comet tails tell stories about the materials being released from the nucleus. The blue-green glow of ion tails comes primarily from ionized carbon monoxide, while the yellowish hue of dust tails reflects the warm light of the sun scattered by countless tiny particles. Occasionally, comets produce tails with hints of red or orange, indicating the presence of other compounds like sodium or iron that have been vaporized from the nucleus and swept into the flowing stream. These subtle color variations are like cosmic fingerprints, allowing astronomers to identify the chemical composition of comets from millions of kilometers away. Each hue represents a different element or molecule that has been liberated from its icy prison and set free to dance in the solar wind. It's a form of celestial spectroscopy where the comet itself becomes a distant laboratory, revealing its secrets through the gentle glow of its own dissolution. The life cycle of a comet tail is as ephemeral as morning mist. When a comet is far from the sun, beyond the orbit of Mars, it remains completely dormant, showing no signs of the spectacular displays to come. As it draws closer and the sun's warmth begins to work its magic, the first faint traces of a coma appear, like the earliest hint of dawn on the horizon. Gradually, almost imperceptibly, the coma grows brighter and more extensive, until finally the solar wind catches hold of the outermost gases and begins to sculpt them into the graceful streams we call tails. The development of a comet's tail is never quite the same twice. Each approach to the sun brings different conditions, different solar wind pressures, different temperatures. The comet itself changes too, as successive passages strip away layers of material and expose new regions of the nucleus to solar heating. A comet that produced a magnificent tail on one visit might appear relatively subdued on its next approach, while another might surprise astronomers by suddenly flaring to unexpected brightness. This unpredictability is part of what makes comet watching such a rewarding pursuit. Unlike the clock and element of cosmic of stars, comets retain work precision of planetary, the steady burning orbits, or spontaneity. They're performers who improvise their shows, creating new variations on ancient themes with each passage through the inner solar system. No two comets are exactly alike, and even the same comet can surprise us with different performances across the centuries. The interaction between comet tails and planetary magnetospheres creates some of the most subtle and beautiful phenomena in our solar system. When a comet passes near a planet with a strong magnetic field, like Jupiter or Saturn, the planet's magnetosphere can deflect and channel the comet's ion tail, creating twisted streams and complex patterns that would be impossible in free space. These interactions are usually too faint to see with the naked eye, but sensitive instruments can detect the delicate braiding of magnetic fields and ionized gas that occurs during these celestial close encounters. Earth's own magnetic field has occasionally interacted with comet tails in ways that produced unexpected auroral displays. When our planet passed through the tail of Halley's Comet in 1910, some observers reported unusual aurora activity at latitudes where such displays are normally never seen. The comet's ionized gases, guided by Earth's magnetic field lines, created ethereal curtains of light that danced across skies from pole to equator. It was as though the comet had left a calling card in our atmosphere, a gentle reminder of its passage through our celestial neighborhood. These tail magnetosphere interactions remind us that space is not the empty void it appears to be, but a dynamic medium filled with invisible fields and flowing particles. The solar wind that shapes comet tails is the same wind that creates the aurora on Earth, that strips away the atmospheres of unprotected planets, and that carries the sun's influence far beyond the orbit of Pluto. Comets make this invisible medium visible, turning the abstract concept of solar wind into streams of light that we can see and appreciate. The study of comet tails has revolutionized our understanding of the space environment throughout our solar system. Before we could send spacecraft to measure the solar wind directly, comets served as natural windsocks, showing us the direction and intensity of this invisible flow. By carefully observing how comet tails behaved at different distances from the sun, astronomers were able to map the solar wind's properties across vast regions of space, creating the first comprehensive picture of our star's extended atmosphere. Even today, with sophisticated space weather satellites monitoring solar conditions around the clock, comets continue to provide valuable data about the solar wind's behavior in distant regions of the solar system. A comet approaching the sun from the Kuiper belt or the Oort cloud carries information about solar wind conditions in regions that no spacecraft has ever visited. Its tail becomes a messenger from the frontier, bringing news of how our star's influence extends into the cosmic deep. The ancient ice that sublimates to form comet tails carries with it isotopic signatures that tell us about conditions in the early solar system. Different isotopes of the same element have slightly different masses, and the ratios between them can reveal information about temperature, pressure, and chemical processes that occurred billions of years ago. When scientists analyze the spectral signatures of comet tails, they're reading a record written in the earliest days of our cosmic neighborhood. These isotopic ratios in cometary material often differ from what we find on Earth, suggesting that comets formed in a different region of the early solar nebula under different conditions. Some comet ice appears to have formed at extremely low temperatures, perhaps in the cold outer reaches of the original disk of material that surrounded the young sun. Other components show signs of having been heated and processed, possibly by shock waves from nearby stellar explosions that occurred while our solar system was still forming. This chemical archaeology helps us piece together the complex history of our solar system's birth. Rather than forming in a single, uniform environment, our cosmic neighborhood appears to have been a dynamic place where materials from different regions mixed and mingled, creating the diverse population of objects we see today. Comets, with their preserved record of these ancient conditions, are like time capsules that allow us to study processes that ended billions of years ago before the first life appeared on Earth. The beauty of comet tails has inspired not just scientific study, but also art, literature, and human contemplation across cultures and centuries. Ancient Chinese astronomers kept meticulous records of broom stars that swept across their skies. while European medieval chroniclers saw in comet tails the swords of angels or the hair of celestial maidens. These poetic interpretations, while scientifically inaccurate, capture something essential about the emotional impact these objects have on human observers. Modern photography has revealed details of comet tails that would have seemed magical to earlier generations. Long exposure images show the intricate structure within these seemingly simple streams, knots, waves, revealing, and discontinuities that speak to the complex physics occurring within the flowing gas. Some photographs capture multiple tails with such clarity that they resemble abstract paintings, cosmic art created by the interplay of gravity, magnetism, and solar radiation. The democratization of astrophotography through digital cameras and computer processing has allowed amateur astronomers to capture images of comet tails that rival those produced by professional observatories. This has created a global community of comet watchers who share their images and observations, creating a collective record of these fleeting celestial events. Each photographer brings their own artistic vision to the task, resulting in a rich variety of interpretations of the same cosmic phenomena. Time-lapse photography of comet tails reveals their dynamic nature in ways that single images cannot capture. Over the course of days or weeks, we can watch as tails grow and shrink, change direction, and develop new structures in response to changing solar conditions. These movies of comet evolution show us that what appears static in a single photograph is actually a constantly changing, living system responding to forces operating across millions of kilometers of space. The ephemeral nature of comet tails makes them particularly poignant subjects for contemplation. Unlike the permanent features of planets or the steady burning of stars, comet tails exist for only brief moments in cosmic time before fading back into invisibility. They remind us that beauty in the universe is often temporary, existing in the spaces between longer periods of dormancy and darkness. This transience makes each appearance more precious, each observation a gift that may not be repeated for generations. As you allow these thoughts of flowing cosmic streams to carry you toward sleep, imagine yourself drifting alongside one of these ancient wanderers as it approaches the sun. Feel the gentle warming of solar radiation beginning to stir the frozen gases beneath your feet. Watch as the first wisps of vapor begin to rise from the surface, catching the sunlight and beginning their long journey into the flowing tail that will soon stretch across millions of kilometers of space. In this peaceful vision, you become part of the comet's story, a witness to the gradual awakening that transforms a cold, dark nucleus into one of the most beautiful sights in the heavens. The tail that forms around you is not just a stream of gas and dust, but a connection between the ancient past and the present moment, between the cold depths of space and the warm heart of our solar system. Let the rhythm of this cosmic transformation guide your breathing as you settle into rest. Like the gentle sublimation of ice into vapor, let your conscious thoughts gradually dissolve into the peaceful flow of dreams. The comet's tail will continue its silent dance through space long after you've drifted off to sleep, carrying with it the same materials that helped create the world beneath your pillow, the air in your lungs and the water in your body. In the vast silence between stars, comets carry messages written in the language of ice and stone. Each nucleus contains a unique mixture of materials that tells the story of where it formed in the early solar system. Some comets are rich in water ice, suggesting they condensed in regions where temperatures were just cold enough for water to freeze. Others contain larger amounts of carbon monoxide or methane ice, indicating they formed even farther from the young sun, in regions so cold that these normally gaseous substances became solid. The diversity of comet compositions creates a kind of cosmic archaeology, where each visitor from the outer solar system brings with it clues about the conditions that existed billions of years ago. When astronomers study the spectra of light emitted by comet tails, they can identify dozens of different molecules, each one a piece of the puzzle that describes how our solar system came to be. It's remarkable to think that these frozen libraries have been preserving this information for so long, waiting patiently in the cold darkness until their moment to share their secrets arrives. The process of outgassing that creates comet tails is surprisingly selective. Different types of ice vaporize at different temperatures, so as a comet approaches the sun, its composition gradually reveals itself in stages. First, the most volatile compounds like carbon monoxide begin to sublimate when the comet is still far from the sun. Then, as temperatures rise, water ice begins to turn to vapor, creating the most prominent part of most comet tails. Finally, as the comet reaches its closest approach to the sun, even less volatile materials like dust and rocky particles are lifted from the surface by the escaping gases. This gradual revelation creates a kind of cosmic striptease, where the comet slowly unveils its hidden nature layer by layer. Each stage of the process tells astronomers something different about the comet's internal structure and composition. The early appearance of carbon monoxide suggests a core rich in these ultravolatile ices. The later emergence of water vapor reveals the main body of frozen water that makes up most comet nuclei. The final release of dust and debris shows us the rocky skeleton that remains when all the ice has been stripped away. Some comets surprise scientists by exhibiting unexpected behaviors during their approach to the sun. Occasionally, a comet that appeared dead and inactive suddenly springs to life, developing a bright coma and spectacular tail with little warning. These outbursts can occur when the sun's heat finally penetrates deep enough to reach a pocket of volatile material that had been protected beneath layers of dust and rock. When this buried ice suddenly vaporizes, it can create pressure that blasts through the overlying material, creating jets and fountains of gas and dust that dramatically brighten the comet. These sudden outbursts remind us that comets are dynamic, evolving objects rather than static chunks of ice and rock. Each passage near the sun changes them in subtle ways, creating new cracks and fissures that may allow heat to penetrate deeper into the nucleus during future visits. Over many orbital cycles, these changes can completely transform a comet's behavior, turning a reliable performer into an unpredictable wildcard that keeps astronomers guessing. The rotation of comet nuclei adds another layer of complexity to their behavior. Most comets spin as they orbit the sun, creating day and night cycles on their surfaces just like planets do. However, comet days can last anywhere from a few hours to several days, depending on how fast the nucleus is rotating. This rotation causes the jets of gas and dust to sweep around the nucleus like the beam of a lighthouse, creating spiral patterns in the coma and sometimes causing the tail to appear twisted or braided. The uneven heating caused by rotation can also create what astronomers call the rocket effect. As gas jets spray from the sun-facing side of the nucleus, they act like tiny thrusters, giving the comet a small push that can gradually change its orbit. Over many passages near the sun, these gentle nudges can add up to significant changes in the comet's path through space. Some comets have had their orbital periods shortened by years due to this effect, while others have been pushed into slightly different trajectories that change when and where they can be seen from Earth. The interaction between a comet's rotation and its outgassing creates some of the most beautiful structures visible in comet tails. As rotating jets sweep around the nucleus, they create spiral patterns in the surrounding coma that can be captured in detailed photographs. These spirals tell astronomers about the comet's rotation period and the location of active regions on its surface. They're like cosmic fingerprints, unique patterns that help identify and track individual comets across multiple apparitions. The seasonal nature of comet activity adds yet another dimension to their complexity. Just as Earth experiences seasons due to its tilted axis, many comets have seasonal variations in their activity levels as different parts of their surface are alternately exposed to and hidden from the sun. A region that was active and producing jets during one part of the comet's orbit may become dormant as the comet's orientation changes, while previously quiet areas suddenly spring to life as they rotate into sunlight. These seasonal effects can create dramatic changes in a comet's appearance over the course of its orbital period. A comet might appear brightest and most active when it's still relatively far from the sun, if that's when its most volatile regions are optimally oriented toward our star. Conversely, it might seem surprisingly dim at perihelion if its active regions happen to be facing away from the sun at that time. This variability makes each comet encounter a unique event, impossible to predict with complete accuracy based solely on the comet's distance from the sun. The study of comet seasonality has revealed that these objects are far more geologically complex than early astronomers imagined. Rather than being uniform balls of ice and dust, comet nuclei appear to have distinct regions with different compositions and activity levels. Some areas are covered with thick layers of dark, rocky material that insulate the ice beneath, while other regions have thin coverings that allow easy sublimation when heated by the sun. These variations create a patchwork of active and inactive terrain across the comet's surface. The gravitational influence of planets can dramatically alter comet orbits, sometimes rescuing comets from the outer solar system and bringing them into more regular, predictable paths. Jupiter, with its enormous mass, acts as a gravitational shepherd for many comets, capturing them into what astronomers call the Jupiter family of short-period comets. These objects have orbital periods of less than 20 years and follow paths that bring them relatively close to the giant planet during each orbit. The process of gravitational capture can be quite violent from the comet's perspective. As a long-period comet approaches Jupiter, the planet's gravity can stretch and distort the nucleus, sometimes causing it to fragment into multiple pieces. The fragments then follow similar orbits, creating families of related comets that share common origins. The famous comet Shoemaker-Levy 9, which crashed into Jupiter in 1994, was one such fragmented comet that had been torn apart by the planet's gravity during a previous encounter. Other planets also play roles in shaping comet orbits, though their effects are generally more subtle than Jupiter's dramatic interventions. Saturn can nudge comets into new trajectories, while the inner planets occasionally provide small gravitational perturbations that accumulate over many orbits. Even Earth has captured a few small comets into temporary satellite orbits, though these objects typically escape after a few years or decades. The complex gravitational dance between comets and planets creates a constantly changing population of objects in the inner solar system. New comets are continuously arriving from the outer reaches, while others are being ejected into interstellar space or destroyed by collisions with the Sun or planets. This dynamic equilibrium means that the comets we see today represent just a snapshot of a much larger, ever-changing population of icy wanderers. The dust left behind by comets as they orbit the Sun creates some of the most reliable and beautiful meteor showers visible from Earth. As our planet passes through these streams of debris each year, we're treated to predictable displays of shooting stars that have been observed and recorded for thousands of years. The Perseids in August, the Geminids in December, and dozens of other annual showers all trace back to specific comets that have been shedding material along their orbital paths for centuries or millennia. Each meteor shower has its own personality, reflecting the characteristics of its parent comet. Some showers produce fast, bright meteors that streak across the sky in brilliant flashes, while others create slower, more colorful displays with meteors that seem to drift lazily through the atmosphere. The differences depend on the size and composition of the dust particles, as well as the speed at which Earth encounters the debris stream. The timing of meteor showers provides a cosmic calendar that has been used by cultures around the world to mark the passage of seasons. The Perseids have been observed for over 2,000 years, their reliable appearance in mid-August serving as a celestial reminder that summer is drawing to a close. Similarly, the Geminids mark the approach of winter solstice with their spectacular December displays, sometimes producing more than 100 meteors per hour at their peak. Modern radar studies have revealed that Earth is constantly bombarded by tiny particles of cometary debris, not just during the major meteor showers, but throughout the year. Most of these particles are so small that they burn up completely in the upper atmosphere, adding their substance to the thin layer of cosmic dust that slowly settles toward Earth's surface. Tons of this is estimated that several material reach our planet every day, making comets a continuous source of extraterrestrial material that subtly enriches our world. The chemistry of meteor showers tells us about the composition of their parent comets in ways that are impossible to study directly. When cometary particles burn up in our atmosphere, they emit light at specific wavelengths that reveal the presence of various elements and compounds. Sodium creates yellow streaks, magnesium produces blue-green trails, and iron adds orange hues to the meteor's glow. By analyzing these colors, astronomers can determine what elements were present in the original comet nucleus. Some meteor showers occasionally produce spectacular displays called meteor storms, when Earth encounters an unusually dense concentration of cometary debris. These rare events can produce thousands of meteors per hour, filling the sky with so many shooting stars that observers describe the experience as watching the heavens fall. The Leonid meteor shower produced such storms in 1833, 1866, and 1966, with the 1833 event being so intense that many people thought the world was ending. The predictability of these cosmic light shows makes them perfect opportunities for peaceful nighttime observation. Unlike comets themselves, which appear irregularly and require telescopes to see clearly, meteor showers can be enjoyed with nothing more than a comfortable chair and a view of the dark sky. They provide a gentle connection to the cosmos that requires no special equipment or expertise, just patience and an appreciation for the subtle beauty of these cosmic visitors burning up in our atmosphere. The trails that meteors leave behind sometimes persist for several minutes after the particle itself has been consumed, creating ghostly streamers of ionized gas that slowly fade in the upper atmosphere. These meteor trains, as they're called, mark the exact path the particle took through the air, creating temporary additions to the night sky that can be photographed and studied. Long exposure photography of meteor showers often captures these trails as graceful streaks that seem to radiate from a single point in the sky, all tracing back to the direction from which the comet debris is approaching Earth. The study of meteor showers has provided important insights into the structure of comet tails and the way material is distributed along comet orbits. By carefully measuring the timing, intensity, and duration of different showers, astronomers can map the density of particles in various parts of the debris stream. This information helps them understand how comets shed material and how that material spreads out over time to create the broad streams we encounter each year. Occasionally, larger fragments from comets survive their passage through Earth's atmosphere and reach the ground as meteorites. These rare specimens provide direct samples of cometary material that can be studied in terrestrial laboratories, using techniques impossible to apply to distant objects. Cometary meteorites tend to be extremely fragile, often crumbling apart soon after they land, but they offer unparalleled insights into the composition and structure of these ancient objects. The water content of some meteorites believed to come from comets has been found to match very closely with the isotopic composition of Earth's oceans, providing strong evidence for the theory that comets delivered much of our planet's water billions of years ago. Other cometary meteorites contain organic compounds including amino acids and other molecules that are building blocks of life, suggesting that comets may have also delivered some of the chemical ingredients necessary for biology to emerge on early Earth. As you continue to drift in this gentle exploration of cosmic wanderers, imagine yourself as one of these tiny particles of ancient ice and dust, liberated from a comet nucleus millions of kilometers from Earth. Feel yourself carried by the solar wind through the cold vacuum of space, part of an invisible stream of debris marking your parent comet's path through the solar system. Years or decades pass as you slowly spread out from your original trajectory, joining countless other particles in a broad river of cosmic dust that will eventually intersect Earth's orbit. Finally, your long journey through space comes to an end as you encounter Earth's atmosphere at tremendous speed. In the fraction of a second it takes for friction to heat you to incandescence, you create a brief streak of light across the night sky, a final moment of glory that connects the ancient past of your comet parent to the present moment of an observer lying peacefully beneath the stars. This cosmic perspective on meteor showers transforms them from simple astronomical phenomena into profound reminders of our connection to the larger universe. Every shooting star represents a small piece of ancient comet material, completing a journey that may have begun millions of years ago in the cold depths of the outer solar system. In that brief flash of light, the past and present merge, creating a moment of beauty that links the observer to the deep history of our cosmic neighborhood. The gentle rhythm of these cosmic connections provides a soothing backdrop for rest and reflection. Like the steady breathing of a sleeping planet, meteor showers mark the passage of time with their predictable annual appearances, creating a calendar written in light across the darkness of space. As you settle into sleep, let the image of these peaceful cosmic visitors guide your thoughts toward dreams of ancient ice and starlight, of patient wanderers carrying messages from the dawn of time across the vast distances that separate us from the cold frontier where comets are born. The gentle dance of gravitational forces that shapes comet orbits operates on timescales that dwarf human comprehension. A single orbit can span millennia, carrying these ancient wanderers through regions of space so distant that the sun appears as merely another star among countless others. During these vast journeys, comets experience temperature variations that would be impossible to survive anywhere on Earth, from the near absolute 0 degrees Celsius to the near absolute 100 degrees Celsius 0 of deep space to the intense radiation of close solar approaches. In the farthest reaches of their orbits, comets exist in a state of perfect preservation, their surfaces unchanged by the passage of centuries. The vacuum of space provides an environment more sterile than any laboratory, where chemical reactions slow to a crawl and physical processes unfold over geological timescales. It's a realm where patience is not a virtue, but a fundamental law of existence, where the concept of urgency has no meaning and everything moves according to the gentle pull of distant gravitational fields. As a comet begins its long fall toward the inner solar system, it passes through invisible boundaries that mark transitions in the solar environment. Beyond the orbit of Neptune, the solar wind is barely detectable, a whisper of particles that carries little energy. But as the comet continues inward, this cosmic breeze gradually strengthens, preparing to sculpt the spectacular displays that will eventually grace our skies. The asteroid belt, that region between Mars and Jupiter filled with rocky debris from the solar system's formation, represents another milestone in a comet's journey toward the sun. Here, the comet encounters a different kind of cosmic environment, one populated by countless chunks of stone and metal that have been orbiting in relative stability for billions of years. The contrast between these rocky asteroids and the icy comet visitors highlights the diversity of materials that formed in different regions of the early solar nebula. Some comets become trapped in this region through gravitational interactions with Jupiter, their orbits modified so that they never again venture into the inner solar system. These objects, known as centaurs, occupy a middle ground between the distant Kuiper belt and the inner planets. They experience moderate solar heating that can trigger occasional outbursts of activity, creating faint comae that mark them as distinct from their purely rocky asteroid neighbors. The transition from comet to asteroid is not always clear-cut. Some objects appear asteroidal when distant from the sun, but reveal comet-like activity when they approach more closely. These discoveries have blurred the traditional boundaries between different types of solar system objects, reminding us that nature rarely fits into the neat categories we create to organize our understanding. The orbital mechanics that govern comet paths follow the same laws that describe planetary motion, but with far more dramatic variations. While planets follow nearly circular orbits that keep them at relatively constant distances from the sun, comets trace elongated ellipses that carry them from the frigid outer reaches to scorching proximity to our star. These extreme orbital geometries create the conditions necessary for the spectacular transformations that make comets visible from Earth. The mathematical elegance of orbital mechanics allows astronomers to predict comet positions with remarkable accuracy, sometimes calculating the exact date and time when a comet will reach its closest approach to the sun years, or even decades in advance. This predictive power transforms comet watching from a game of chance into a scheduled appointment with cosmic beauty, allowing observers to plan and prepare for these celestial encounters. The concept of orbital energy provides another lens through which to appreciate comet behavior. Objects in the outer solar system possess enormous amounts of gravitational potential energy by virtue of their distance from the Sun. As they fall inward, this potential energy converts to kinetic energy, causing the comet to accelerate as it approaches perihelion. The fastest comets can reach speeds exceeding 50 kilometers per second as they whip around the Sun, only to slow again as they climb back toward the outer darkness. This cosmic roller coaster of acceleration and deceleration creates natural rhythms in comet evolution. The brief periods of intense solar heating near perihelion drive the spectacular activity that creates tails and comet, while the long, slow journey through the outer solar system provides time for the nucleus to cool and stabilize between active periods. It's a cycle of awakening and dormancy that has repeated countless times since the solar system's formation. The gravitational influence of planets creates perturbations in comet orbits that can accumulate over many passages, sometimes leading to dramatic changes in orbital periods or even ejection from the solar system entirely. These planetary encounters add an element of chaos to what might otherwise be perfectly predictable motion, ensuring that each comet follows a unique evolutionary path through space and time. Jupiter's massive gravitational field makes it particularly effective at altering comet orbits. The planet acts as a kind of cosmic traffic controller, deflecting some comets into shorter periods while flinging others out of the solar system forever. This ongoing process of capture and ejection helps maintain a steady population of observable comets in the inner solar system, replenishing losses due to sublimation and fragmentation, with fresh arrivals from the distant reservoir of the Oort cloud. The study of comet orbit evolution has revealed that many of the comets we see today have been visiting the inner solar system for thousands or even millions of years. Each passage has subtly altered their composition and structure, stripping away the most volatile materials and leaving behind increasingly refractory cores. These evolutionary changes mean that older comets often produce less spectacular displays than fresh arrivals from the outer regions, their most dramatic materials having been exhausted during previous approaches to the Sun. The relationship between comet brightness and distance from the Sun follows predictable patterns that allow astronomers to estimate how spectacular a particular comet will appear. Generally, brightness increases rapidly as comets approach the Sun, following mathematical relationships that account for both the increased sublimation of ices and the enhanced scattering of sunlight by the expanding coma. However, individual comets often deviate from these predictions, sometimes dramatically due to unique characteristics of their composition or structure. Comet hunting has become a passionate pursuit for amateur astronomers around the world, who systematically scan the skies in search of new visitors from the outer solar system. The discovery of a new comet brings with it the excitement of finding something that has never been seen before, an object that may be making its first visit to the inner solar system in millions of years. These discoveries often carry the names of their finders, creating a personal connection between observer and cosmic wanderer that can last for generations. The patient work of comet hunters requires dedication that mirrors the patient journeys of the comets themselves. Many discoverers spend years methodically photographing the same regions of sky, comparing images to detect the slow motion that betrays a distant comet's presence. It's a meditative practice that rewards persistence and attention to detail, qualities that seem particularly appropriate for studying these ancient, unhurried travelers. Modern automated sky surveys have revolutionized comet discovery, using sophisticated cameras and computer algorithms to detect moving objects across vast areas of sky each night. These robotic systems can identify potential comet candidates much faster than human observers, but they still require careful follow-up observations to confirm discoveries and determine orbital characteristics. The marriage of technology and human curiosity continues to expand our catalog of known comets at an unprecedented rate. Each new comet discovery adds another data point to our understanding of the outer solar system's population and structure. Statistical analysis of comet orbits and compositions helps astronomers refine models of how the solar system formed and evolved, while individual objects often provide surprises that challenge existing theories. The ongoing process of discovery ensures that comets remain active subjects of scientific inquiry rather than merely historical curiosities. The nomenclature of comets reflects their discovery history and orbital characteristics through a systematic naming convention that can seem arcane to casual observers. Periodic comets receive numbers and names that indicate their orbital periods and discoverers, while long of discovery and by the year period comets are designated additional letters that show the order of discovery within that year. These technical designations often give way to more colorful popular names that capture public imagination and make the objects more accessible to non-specialists. The cultural impact of bright comets extends far beyond their scientific importance, inspiring art, literature, and philosophical reflection across human history. The appearance of a spectacular comet has traditionally been seen as a portent of change, a celestial messenger announcing significant events in human affairs. While we now understand the natural causes behind comet appearances, their capacity to inspire awe and contemplation remains undiminished by scientific knowledge. The democratization of astronomical imaging through digital photography has allowed unprecedented numbers of people to capture and share images of comets, creating a global community of observers who collectively document these transient phenomena. Social media platforms become galleries of comet photography during major apparitions, with contributors from every continent sharing their perspectives on the same cosmic visitor. This collective documentation creates a richer record of comet behavior than any single observer could produce alone. Time-lapse sequences of comet development reveal the dynamic nature of these objects in ways that static images cannot convey. Over periods of weeks or months, we can watch as nuclei brighten, comae expand, and tails develop and evolve in response to changing solar conditions. These cinematic records of comet evolution provide invaluable data for researchers, while also creating some of the most beautiful astronomical imagery ever captured. The psychological impact of observing comets seems to transcend their physical characteristics, touching something fundamental in human nature that responds to celestial beauty and mystery. Perhaps it's their temporary nature that makes them so compelling. The knowledge that this particular display of cosmic artistry will fade and may not return for generations. Or perhaps it's their connection to deep time and distant space that puts our earthly concerns into cosmic perspective. The meditative quality of comet observation makes it particularly suitable for peaceful evening contemplation. Unlike planets, which require telescopes to reveal interesting details, or stars, which remain essentially unchanged from night to night, comets offer naked-eye beauty that evolves slowly enough to reward patient observation. Spending time with a comet becomes a form of cosmic companionship, a shared journey through space with an ancient traveler from the solar system's frontier. The seasonal timing of comet apparitions often enhances their emotional impact, with winter comets appearing in cold, clear skies that emphasize their otherworldly nature, while summer visitors seem to dance among the warm constellations of the season. The relationship between celestial mechanics and terrestrial seasons creates natural associations between particular comets and specific times of year, adding temporal depth to the experience of comet watching. The legacy of great comets extends beyond their periods of visibility, living on in photographs, paintings, and written accounts that preserve their beauty for future generations. Historical records of bright comets provide valuable scientific data about these objects' past behavior while also documenting the human response to cosmic spectacle across different cultures and eras. These archives remind us that comet watching is both a scientific endeavor and a deeply human experience that connects us to observers throughout history. As you allow these thoughts of patient cosmic wanderers to settle into the quiet corners of your mind, imagine the profound stillness of space through which these ancient objects move. In that vast silence, broken only by the whisper of solar wind and the gentle pull of distant gravity, comets follow their predetermined paths with the serenity that transcends human understanding of time and motion. The darkness between stars holds countless such travelers, each carrying its own cargo of primordial ice and dust, through journeys measured in millennia rather than years. Some approach the warmth and light of stars for brief moments of glory, while others remain forever in the cold depths, their beauty unseen and their stories untold. In this cosmic democracy of ice and stone, every object follows its own path according to the fundamental laws that govern all motion in the universe. Let the rhythm of these vast orbital cycles guide your thoughts as consciousness gently fades toward sleep. Like comets themselves, your awareness can travel great distances through the landscape of dreams, visiting strange territories of imagination before returning to the familiar shores of waking life. The same forces that shape comet orbits, patient and inexorable, work their gentle influence on the tides of sleep and dream that carry you through the night toward morning's return. In the space between sleeping and waking, you might find yourself drifting alongside these cosmic wanderers, feeling the slow pulse of gravitational forces that have shaped their paths since the solar system's birth. The ice beneath your feet holds the memory of stellar nurseries and molecular clouds, while the vacuum around you carries the faint traces of solar wind that will eventually sculpt tales of impossible beauty from the frozen materials of your traveling companion. The patience required to appreciate comet timescales mirrors the gentle approach to sleep itself, where rushing toward unconsciousness only delays its arrival. Like comets in their distant orbits, the mind must be allowed to follow its natural cycles, gradually releasing the concerns of the day as it drifts toward the restorative darkness of deep sleep. In this cosmic perspective, sleep becomes not an interruption of consciousness, but another phase in its endless orbital dance around the cycles of day and night. The gentle gravitational embrace that guides comets through their eternal journeys creates what astronomers call orbital resonances. invisible patterns that connect the motion of different objects across vast distances. Some comets find themselves locked in these cosmic rhythms with planets, completing 2 orbits for every 3 of Jupiter's, or maintaining other mathematical relationships that keep them in stable, predictable paths for millions of years. It's as though the solar system itself is a vast musical instrument, with each object contributing to a harmony too slow and subtle for human ears to perceive directly. These resonances create safe harbors in the chaotic gravitational environment of the solar system, allowing certain comets to maintain stable orbits despite the competing influences of multiple planets. The mathematics underlying these relationships reveal an unexpected order within apparent randomness, showing that even the most distant and seemingly wayward comet follows rules as precise as those governing the movement of clock hands or the phases of the moon. The discovery of these orbital patterns has revolutionized our understanding of solar system dynamics, revealing that what appears to be random motion is actually part of an intricate choreography that has been unfolding for billions of years. Each comet's path is influenced not just by the sun's gravity, but by the combined gravitational effects of all the planets, creating a complex web of forces that can be mapped and predicted using sophisticated mathematical models. The beauty of these celestial mechanics lies in their underlying simplicity despite their apparent complexity. Every comet follows the same fundamental laws of motion that govern falling apples and orbiting planets. Yet the interplay of multiple gravitational sources creates trajectories of stunning elegance and infinite variety. No 2 comets follow identical paths, yet all obey the same universal principles that connect the smallest pebble to the largest galaxy. The concept of gravitational wells helps visualize how comets navigate through the solar system's complex landscape of forces. Imagine space as a vast rubber sheet with massive objects like the sun and planets creating deep dimples that nearby objects tend to roll toward. Comets trace paths along the contours of this warped space-time, sometimes spiraling inward toward a gravitational well. Other times climbing out toward the flatter regions where weaker forces allow more leisurely travel. This geometric interpretation of gravity transforms the abstract mathematics of orbital mechanics into something almost tangible, allowing us to envision how comets experience their journeys through space. A comet falling toward the sun rushes down an increasingly steep gravitational slope, gaining speed as it approaches perihelion before climbing back up the opposite side of the well toward the distant regions, where it will eventually slow to a crawl before beginning its next descent. The 3-dimensional nature of comet orbits adds another layer of complexity to these gravitational interactions. Unlike planets, which mostly orbit in the same plane as Earth's path around the sun, comets can approach from any direction, their orbital planes tilted at random angles that reflect the chaotic conditions in which they formed. This freedom to move in 3 dimensions creates orbital geometries that can seem impossibly complex when viewed from our Earthbound perspective. Some comets follow retrograde orbits, traveling around the sun in the opposite direction from the planet's motion. These backwards wanderers create particularly spectacular displays when they encounter Earth's orbit, since their relative velocity is much higher than comets moving in the same direction as our planet. The increased speed of these encounters can create meteor showers with unusually fast, bright shooting stars that streak across the sky with distinctive characteristics. The inclination of comet orbits to the plane of the solar system creates seasonal variations in visibility from Earth. A comet with a highly tilted orbit might be perfectly placed for observation from the northern hemisphere during one part of its approach, then shift to southern skies as it continues along its path. This geometric dance between comet orbits and Earth's position creates opportunities for observers in different parts of the world to enjoy optimal viewing conditions at different times. The study of comet orbit families has revealed fascinating relationships between objects that might appear completely unrelated. Some comets share similar orbital characteristics because they originated from the fragmentation of a single larger object, while others have been gradually shepherded into similar paths by repeated gravitational encounters with the same planet. These invisible connections create a kind of cosmic genealogy that links objects across vast distances and time spans. The precision required to calculate comet orbits accurately demonstrates the remarkable power of mathematical prediction in astronomy. Using nothing more than careful observations of a comet's position over several nights, astronomers can determine its complete orbital path, predict when it will return, and even estimate how bright it will become during future apparitions. This ability to see into the cosmic future represents one of science's most elegant achievements. The perturbations that planets cause in comet orbits sometimes produce unexpected benefits for Earth-based observers. A gravitational encounter with Jupiter might alter a comet's path just enough to bring it closer to Earth than originally predicted, creating a more spectacular display than initially anticipated. Conversely, planetary influences can sometimes deflect comets away from favorable viewing positions, turning what might have been a bright, naked-eye comet object into a telescopic target. The long-term evolution of comet orbits reveals the dynamic nature of our solar system over geological timescales. Objects that are currently in stable orbits may be gradually spiraling toward the Sun due to non-gravitational forces, while others are slowly being ejected toward interstellar space. This ongoing cosmic recycling ensures that the population of observable comets changes continuously, with new arrivals replacing objects that have been lost to sublimation or gravitational ejection. The influence of galactic tides on comet orbits operates on timescales so vast that they're difficult to comprehend from a human perspective. As our entire solar system orbits the center of the Milky Way galaxy, it experiences subtle gravitational influences from nearby stars and the galaxy's overall mass distribution. These forces can occasionally nudge comets in the distant Oort cloud toward the inner solar system, triggering showers of new comets that arrive over periods of millions of years. The concept of comet reservoirs helps explain the continuous supply of these objects despite their tendency to be destroyed or ejected during repeated passages near the Sun. The Kuiper Belt, a region beyond Neptune populated by icy objects left over from solar system formation, serves as a source of short-period comets, while the much more distant Oort cloud provides the long-period visitors that can appear without warning after millions of years in deep space. Recent discoveries have revealed that the boundary between comets and asteroids is less distinct than previously thought. Some objects in the outer asteroid belt occasionally develop comet-like activity when solar heating vaporizes subsurface ice deposits, while certain comet nuclei appear to be covered with rocky material that gives them asteroid-like appearances when inactive. These findings suggest that the solar system contains a continuum of objects with varying proportions of ice and rock. The rotational dynamics of comet nuclei create fascinating patterns in their outgassing behavior. As a comet spins, different regions of its surface alternately face toward and away from the sun, creating cycles of activity that can cause the coma and tail to brighten and fade with the nucleus's rotation period. Some comets exhibit such regular variations that astronomers can use them as cosmic clocks, measuring rotation rates from millions of kilometers away. The discovery of binary comets, objects consisting of two separate nuclei orbiting around their common center of mass, has revealed another layer of complexity in these ancient systems. These cosmic pairs may have formed through gentle collisions in the outer solar system, or they might represent fragments of larger objects that were disrupted by tidal forces during close planetary encounters. Their synchronized dance through space creates double displays of comet activity when both nuclei become active simultaneously. The seasonal behavior of comets extends beyond simple distance-based heating effects to include complex interactions between different volatile compounds within the nucleus. Early in a comet's approach to the sun, the most volatile substances like carbon monoxide begin to sublimate, creating initial activity that may be barely visible from Earth. As heating continues, water ice begins to vaporize more rapidly, producing the bright displays that make comets famous. Finally, near perihelion, even relatively stable compounds may begin to break down, sometimes causing dramatic outbursts of activity. The composition gradients within comet nuclei create layered structures that reveal themselves gradually as solar heating penetrates deeper into the interior. The outer layers, processed by repeated solar heating during previous orbits, may be depleted in volatile materials and enriched in dust and refractory compounds. Beneath these altered surfaces lie more pristine materials that retain the original composition from the comet's formation billions of years ago. The sublimation physics that drives comet activity operates according to principles that can be observed and studied in terrestrial laboratories. Yet the extreme conditions in space create behaviors that would be impossible to replicate on Earth. The near-perfect vacuum surrounding comet nuclei allows sublimated gases to expand freely without the pressure constraints that would limit similar processes in our atmosphere, creating the vast coma and tails that make these objects so spectacular. The interaction between sublimating gases and dust particles within comet nuclei creates complex feedback mechanisms that can dramatically influence activity levels. As gas escapes from beneath the surface, it can lift and carry dust particles along, but if too much dust accumulates in certain areas, it can insulate underlying ice and reduce further sublimation. This balance between gas production and dust mantling helps determine which regions of a comet's surface remain active and which become dormant over time. The chemical reactions that occur within comet Comet-E as solar radiation breaks down simple molecules create some of the most exotic chemistry in the solar system. Water vapor dissociates into hydrogen and oxygen atoms. Carbon monoxide breaks apart to form carbon and oxygen, and complex organic molecules fragment into simpler components. These reactions create the characteristic colors and spectral signatures that allow astronomers to identify the parent molecules even after they've been destroyed by solar energy. The plasma physics of comet ion tails involves processes similar to those occurring in Earth's magnetosphere and the solar corona, making comets natural laboratories for studying fundamental plasma phenomena. The interaction between solar wind particles and ionized comet gases creates magnetic field configurations, shock waves, and particle acceleration mechanisms that help scientists understand similar processes occurring throughout the universe. The dust dynamics within comet tails follow principles of celestial mechanics, modified by radiation pressure and electromagnetic effects. Larger particles are less affected by solar radiation pressure and tend to follow trajectories closer to the comet's orbital path, while smaller grains are pushed more directly away from the sun. This size sorting creates the curved dust tails that trace the comet's motion through space, while simultaneously responding to solar radiation forces. The optical properties of comet dust reveal information about particle sizes, compositions, and structures through the scatter and absorb sunlight. Different minerals produce characteristic spectral features, while particle size distributions affect the overall brightness and color of the scattered light. By analyzing these optical signatures, astronomers can determine what types of materials are being released from comet nuclei and how those materials are distributed within the expanding coma. The formation of comet jets results from highly localized sublimation processes that create focused streams of gas and dust emanating from specific points on the nucleus surface. These jets can persist for hours or days, creating fountain-like displays that can be photographed and studied in detail by spacecraft. The direction and intensity of jets depend on factors including local composition, surface topography, and the orientation of the nucleus relative to the sun. The pressure variations created by outgassing can cause significant stresses within comet nuclei, sometimes leading to fractures, landslides, and other geological processes despite the very low gravity environment. These internal forces can reshape the surface topography over time, creating the varied landscapes observed on comet nuclei by visiting spacecraft. Cliffs, valleys, and boulder fields all testify to the dynamic nature of these seemingly inert objects. The thermal properties of comet nuclei determine how quickly solar heat can penetrate into their interiors and drive sublimation processes. Materials with low thermal conductivity act as insulators, preventing heat from reaching deeply buried ice deposits, while more conductive substances allow thermal energy to spread more readily through the nucleus. These variations in thermal properties help explain why different regions of the same comet can exhibit vastly different activity levels. The magnetic properties of comet nuclei and their interaction with the solar wind's embedded magnetic field create complex electromagnetic environments around active comets. These interactions can accelerate charged particles to high energies, create radio emissions detectable by Earth-based instruments, and influence the structure and dynamics of comet tails in ways that are still being studied and understood. As you drift deeper into this cosmic reverie, imagine yourself floating in the gentle embrace of one of these ancient wanderers as it makes its slow journey through the outer reaches of space. Feel the profound stillness of the vacuum around you, broken only by the occasional whisper of escaping gas as solar radiation gradually warms the frozen surface beneath your feet. The stars wheel slowly overhead, their patterns shifting almost imperceptibly as your comet follows its predetermined path through the galaxy's spiral arms. The ice around you holds memories older than Earth itself, preserving in its crystalline structure the chemical signatures of stellar explosions that enriched the early solar nebula with heavy elements. Carbon atoms that once burned in the hearts of massive stars now rest quietly in frozen carbon dioxide, waiting for their moment to sublime into the vacuum and catch the sunlight in displays of ethereal beauty. Time moves differently here in the realm of deep space, where a single orbit can span millennia and theancy has no meaning. Your concept of Comet companion has been following this same path for countless eons, patient and unhurried in its cosmic dance with gravity and inertia. The rhythm of its journey matches the deeper rhythms of the galaxy itself, part of a vast clockwork that has been ticking since the universe was young. The silence is profound and complete, unmarred by the atmospheric disturbances that create sound on planets. In this perfect quiet, you can almost sense the subtle gravitational tugs of distant planets, the gentle pressure of solar radiation, and the slow internal movements as temperature variations cause the nucleus to expand and contract imperceptibly. Every process unfolds with the unhurried pace of geological time, where minutes and hours blend into the larger flow of cosmic evolution. As your awareness settles into this timeless perspective, let the steady progression of your comet's orbit guide your thoughts toward the peaceful rhythms of sleep. Like the ancient ice around you, your mind can find rest in the deep cold of unconsciousness, preserving the day's experiences in the crystalline structures of memory, while allowing your body to restore itself in the perfect vacuum of dreamless sleep. The darkness between stars becomes a blanket that wraps around your consciousness, soft and encompassing as the cosmic dust that surrounds your celestial vessel. In this profound quiet, where the only motion is the imperceptible progress along an orbit measured in astronomical units, you can release all earthly concerns and drift into the same patient stillness that has carried comets through space since the dawn of the solar system. The gravitational forces that shape your comet's path work their gentle influence on the landscape of dreams as well, creating currents and tides in the ocean of sleep that carry you through the night's journey toward morning. Like a comet approaching perihelion, your rest deepens as you draw closer to the restorative center of the sleep cycle, gathering the energy you'll need for tomorrow's return to the warmth and activity of waking life. The tail that streams behind your comet in this peaceful vision becomes a trail of released thoughts and worries, sublimated away by the gentle heat of relaxation and carried off by the solar wind of rest. What remains is the essential core of yourself, traveling serenely through the night sky of consciousness, following the natural laws that govern both cosmic motion and the cycle of sleep and waking that connects all living things to the larger rhythms of the universe. In this cosmic meditation, you become both observer and participant in the ancient dance of matter and energy that has been unfolding since the first stars began to shine. The same forces that guide comets through their patient orbits work their influence on every atom in your body, every electrical impulse in your brain, connecting you to the vast web of physical law that unites all things from the smallest particle to the largest galaxy. Let this sense of cosmic connection carry you gently toward the horizon of sleep, where consciousness fades like a comet's tail as it moves away from the sun's warming influence. In the cold depths of space where comets spend most of their existence, there is perfect peace and perfect stillness, a model for the deep rest that awaits you in the hours before dawn, returns to restore the warmth and light of a new day. The ancient chemistry preserved within comet nuclei tells stories that predate the formation of our solar system itself. Deep within their frozen hearts lie materials that condense directly from the interstellar medium, tiny grains of dust and ice that witnessed the birth and death of stars long before our sun began to shine. These microscopic capsules carry isotopic time signatures that reveal the conditions present in the stellar nursery, where our cosmic neighborhood first took shape. When scientists analyze the spectral signatures of light emitted by comet tails, they're reading a chemical library written in the language of atoms and molecules. Each wavelength of light corresponds to a specific element or compound, creating fingerprints that allow researchers to identify materials that formed under conditions impossible to recreate on Earth. Organic molecules of surprising complexity have been detected in comet spectra, including some that serve as building blocks for the proteins and nucleic acids essential to life. The preservation of these delicate chemical structures over billions of years speaks to the remarkable stability of the deep space environment. In the frigid vacuum beyond Neptune's orbit, chemical reactions proceed at rates so slow that complex molecules remain essentially unchanged from their original form. It's as though each comet carries within its nucleus a perfectly preserved sample of the primordial materials from which everything in our solar system eventually formed. The water ice that makes up the bulk of most comet nuclei contains dissolved gases that were trapped during the original freezing process billions of years ago. When this ice finally sublimates near the sun, these ancient gases are released, carrying with them information about the pressure and temperature conditions that existed in the outer regions of the early solar nebula. The ratios of different isotopes in this water provide clues about the stellar processes that created the heavy elements we see throughout the solar system. Some comet nuclei contain layers of different materials, like geological strata that record changing conditions during their formation. These layers may represent different episodes of accretion, periods when the growing comet nucleus collected materials from different regions of the solar nebula or during different phases of the sun's early evolution. The boundaries between layers can be detected through variations in outgassing behavior as solar heating reaches different depths within the nucleus. The organic chemistry occurring within comet nuclei involves reactions between simple molecules that have been proceeding at imperceptibly slow rates for geological ages. Cosmic radiation gradually breaks down some compounds while facilitating the formation of others, creating a slow-motion chemical evolution that transforms the nucleus composition over millions of orbital cycles. This process may actually increase the complexity of organic molecules over time, potentially creating compounds that were not present when the comet first formed. The discovery of amino acids in comet samples has profound implications for understanding how life's building blocks became distributed throughout the early solar system. These complex organic molecules, which form the basis of proteins in all known life forms, appear to form naturally in the cold, radiation-rich environment of comet nuclei. The delivery of such molecules to early Earth through comet impacts may have provided a crucial head start for the chemical processes that eventually led to the emergence of life. As we reach the end of our gentle journey through the cosmos, we've traveled alongside these ancient messengers from the dawn of time, witnessing their patient dance through the darkness and their moments of brilliant awakening near the sun. These frozen libraries of cosmic history carry within them the very materials that shaped our world and perhaps sparked the first stirrings of life itself. Tonight, as you drift toward sleep, let the rhythm of their eternal orbits guide you into peaceful rest, knowing that somewhere in the vast silence of space, these timeless wanderers continue their graceful voyage through the stars.